Thanks everybody for coming along, and to those listening on Zoom. Let me plead your indulgence for this because it's not a very well organized or prepared or planned or generally much good as a talk. What I'm doing here is trying to put some material together for a book that I'm writing on explanation in physics, and in particular, this is going to be some material on interventions in physics and on kind of the possible applications of very low amplitude chance events coming from quantum theory in metaphysics. And the idea is that sometimes these very low probability quantum events have been seen as a problem. I would say they're also an opportunity to do interesting theorizing. So here goes. This is kind of an overview of what's going to happen. I'm going to point out that not just quantum theory, but actually classical theory already offer plenty of low amplitude, low probability events that can be used in certain metaphysical applications. But that quantum theory does better than classical physics at giving us really thoroughgoing, systematic, kind of unlikely enough events to really do a lot of work in these theories. And once we start applying interventionist approach to causation as an account of causation in fundamental physics, and once we start looking at what the interventions we might need to do that are, and once we start looking for and finding them in quantum theory, we're going to end up with a notion of intervention which I think is fit for purpose, but which is very, very different from the notion of an intervention which comes up more ordinarily when one is thinking about interventionist accounts of causation. The kind of interventions I have in mind are definitely not the kind of thing anybody could do. They're not the kind of things that get done. They're the kind of things that just happen. And moreover, they're the kind of things that almost certainly won't just happen. So they're kind of peculiar things, and calling them interventions, maybe that's to stretch the term too far. But the question is, can they do the same sort of work in a philosophical theory that interventions do? That's the suggestion. So here's the structure of the talk. I'm going to talk, first of all, kind of warm up about some what I call modally distant classical possibilities, and then some modally distant quantum possibilities. And then I'm going to talk about how those modally distant quantum possibilities can counter interventions, giving us quantum interventions, and then a certain species of them that are going to be the kind of the grandest of all these cosmological quantum interventions. I guess I should have been cosmological quantum interventions there, but hopefully you get the idea. So to start with, just to kind of bit of a reality check, there's already a lot of really unlikely things that classical physics permits to happen. And one way you get something unlikely is just by chaining together enough chance events. So it's true that any sequence of coin tosses, heads, tails, tails, heads, 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 tails, or just heads all the time, is as likely as any other. But nonetheless, there's a certain global property of the lands heads every time outcome that is very surprising. And if you were to toss a coin 10,000 times and it was to land heads every time, you would become rationally certain or nigh on certain that there was something funny about the coin or about the situation in which you were tossing it. That kind of stuff can happen by chance, but it just is nearly always going to be more rational to believe there's an explanation going on for how it happened than that it just did happen by chance. There's a film, Wavefunction and Guildernstern Are Dead, where heads is tossed repeatedly by one of the protagonists on a coin, and it gets more and more worked up because this is too weird, something strange is going on. But the friend is nonplussed, and it's like each of them could just as easily have landed heads as tails, so nothing surprising has ever happened. And all of that, the point is just as classical as you like. As long as you can have, you can model a coin toss successfully, you can get really, really, really unlikely events just by iterating ordinary outcomes. You can actually kind of do the kind of reverse thing. You can take an event, no matter how uneven its chance is, and turn it into a coin with equal chances, effectively. There's no paper by Al Hayek that show how you can kind of go in the reverse direction to go from any event you like to a fair coin, effectively. But this is the opposite direction. Once you've got a fair coin or something like it, you can get to any probability you like using it. And there's nothing particularly quantum about that. I mean, there's nothing at all quantum about that. As long as you get probability at all in classical physics, you can get probabilities, you can get outcomes that are as unlikely as you like. And even though that doesn't guarantee we're going to get all sorts of those outcomes, statistical mechanics gives us apparently a kind of guarantee that we will have enough variety in those unlikely outcomes to do what we want with. So this kind of classic example from StatMech is the idea that there's a small but non-zero possibility that all the air, which is currently happily kind of distributed evenly throughout the room, might kind of concentrate itself up into one corner and stay there for long enough that we all suffocate to death in the meantime, or or maybe worse things happen in the vacuum that we find ourselves left in. It wouldn't be very nice. But you get that from the fact that classical mechanics is continuous, along with a hypothesis that I'm calling the independence assumption after Key and Dorr, about how close I'm not going to try to reconstruct the content of this assumption, and I suspect Katie is the person that should have those questions directed to anyway. But it's related to the way in which there's kind of a lack of correlation between the kind of macroscopic conditions that obtain here now. The thought is there isn't anything macroscopically distinctive about the histories which lead to the bizarre outcomes from a state like now. They are kind of distributed kind of evenly amongst the microstates corresponding to the current macrostate, but there are ones where weird things happen. It's not that there's kind of a tightly constrained region of microstates that are all and only the ones that lead to weird behavior. The weird behavior microstates are kind of distributed evenly amongst the microstates corresponding to the any given macrostate. And that's what is going to offer you the kind of guarantee that these sorts of processes that you can describe at a macroscopic level as having a kind of if you can identify some microhistory that is like a possible future continuation of a macrostate like the one we're in, then you can be assured that there will be like non-zero StatMech probability attaching to these really low probability outcomes that you've characterized that way. So moving into the second example, somebody walking on water. One way that could happen would be if the motions of the particles in the water happen to be such as to lead to a great upwelling of water in just the right place to be where you put your foot at the moment you put it down. And so that holds your weight up for just long enough to take a step and put your foot somewhere else, and then there is a great upwelling of water there. And we can describe those sorts of histories microphysically, and we can observe that they don't violate conservation principles at the global level. They needn't do that. And so these sorts of assumptions about StatMech are going to give us the possibility of that sort of outcome. And in general, like once you can have this, you can have all sorts of processes going very differently from how they actually go. Diffusion can act in reverse, decay can act in reverse, and pretty much anything. So I've got this phrase elemental magic, and kind of the magic you see people doing sometimes in like, is there a show called Avatar? I think I haven't watched this, but I'm told that there's a lot of like people harnessing the elements in this show. Basically, lots of the stuff that's happening there, where like water rises in a water spout and like bashes a bad guy or something, that can happen. And it can happen in a world where somebody raises their hand and says, I command this water to rise up and bash the bad guy. It just doesn't happen kind of in a magical way. It just kind of happens spontaneously right after somebody did that incantation. So pretty much anything that you can describe that's not violating like global conservation laws is something that there's a more or less remote StatMech possibility for. Yeah, so control of the elemental forces of earth, air, wind, and fire. These are all statistical mechanical systems, and so they can display this deviant behavior. So there's a lot of weird stuff that is physically possible in that vision. And Dorr's paper is applying that to give a kind of miracle-based semantics for, a miracle-free semantics for counterfactuals that replaces the kind of Lewis-style miracles approach. So for Dorr, if something had been different in such a way that this weird stuff had happened, it would have been different all the way back to the beginning of time. Just that difference would have been macroscopically invisible until very recently. But we can talk about that at counterfactuals later if you want. So one thing that comes up already here is that these sorts of weird modally distant possibilities can give us plenty of misleading evidence that would completely ruin physics. So if we toss a fair coin often enough, lands every time, it's overwhelmingly rational to believe that coin's biased. If like bizarre anti-thermodynamic behavior was to occur just by chance every time that we tried to run a test of thermodynamics, or even to observe in a systematic way any phenomena related to thermodynamics, then we would have a very misleading set of evidence, and we would come to believe that thermodynamics was in fact false. Maybe we wouldn't have, we would just have not ended up with a belief in thermodynamics like the present belief we have in it. And moreover, like, if every time someone tried to walk on water, having said a prayer beforehand, they successfully walked on water in this way, the water did move in just the right way to keep them up. And every time they didn't say a prayer beforehand and then attempted to walk on water, it didn't work, we would quite reasonably conclude that the prayer is making a difference here, and in fact that there is some kind of supernatural explanation going on. That would be the reasonable thing to believe in that situation. And this takes us to a kind of, this is an example that Ned Hall uses against Mark Lang. Mark Lang's theory of counterfactuals predicts that if Jesus had walked on water, it wouldn't have been a miracle, it would have been a thermodynamic oddity of this kind of style. Whereas Hall thinks it's kind of obvious that if Jesus had walked on water, it would have been a miracle. That's actually true. Because like the closest way in which Jesus walks on water is by divine magic. And so Lang's view of counterfactuals is not actually capturing. This is an objection that Hall makes to Lang's view of counterfactuals. But it doesn't have to be seen as an objection. It might well be that if Jesus had walked on water, it would have been one of these thermodynamic odd events, and everybody would have formed the same beliefs they in fact formed. So the lesson here is that these low probability outcomes can give super misleading evidence. And that's true even pre-quantum cases. So there's a kind of family of objections to certain accounts of quantum probability that say there's all these deviant low probability outcomes that give us completely misleading evidence that would undermine quantum probability. And I think we need to be very careful about that sort of objection, because those sorts of objections can already be made in the classical case. We don't take it to undermine classical accounts of probability. But that's a bit of a digression. So now we're moving into the quantum case, these modally distant quantum probability possibilities, and into these things that are called tails of the wave function. So the quantum dynamics is linear, and it evolves in a unitary way. And what that means is that kind of possibilities tail off gradually. They rarely fall sharply to zero. If you want to find out what the probability is for finding some given particle around here, then that's like some like dust particle or something that's quite well localized, but not perfectly localized, then like the chance of you finding it here is relatively high. The chance of you finding it over here is much lower. The chance of you finding it over here is way lower still, but non-zero. And the chance of you finding it kind of around the block is still non-zero. Gets kind of falls off really radically fast, but not all the way to zero. And these sorts of wave function tails cause all sorts of interpretive problems for interpretations that want it to be zero, that like want unactualized possibilities to be non-existent rather than just negligible. But for my purposes, all I'm doing is noting them. Because of wave function tails, we are going to get, through the same sort of reasoning as in the StatMech case, bizarre possibilities of any kind that we can give like a clear microscopic characterization of, coming out as having some non-zero quantum chance. And the most familiar kind of thing, maybe this is like the generic case, maybe this is just one special case, but I'd be interested if there are cases that we should kind of don't want to think of in terms of tunneling. Give us modally distant quantum probability possibilities. It doesn't have to be that modally distant, like the chance doesn't have to be that low. And because alpha decay is an instance of quantum tunneling, the alpha particle like is kept inside the nucleus by a radioactive nucleus by an energy barrier. It kind of has to borrow energy, so to speak, to cross that barrier and get out the other side. But every now, classically, that couldn't happen. So classically, radioactive nuclei would be, alpha radioactive nuclei would be stable. But they're not, because in quantum mechanics, these particles can tunnel through the energy barrier. And in principle, there's no limit on how big an energy barrier can be tunneled through in that way, or kind of how far it can cross, how wide that barrier can be, as long as it's an energetically allowed state once it reaches the other side. That's something that gets a non-zero probability. And so in the same sort of way, this kind of scenario can give rise to misleading evidence. There's lots of quantum experiments that we did that we in fact gave us evidence of quantum theory over classical theory. But there are ways in which those quantum experiments could have turned out that would have kind of simulated the results of the classical experiments. And so the quantum possibilities also, no big surprise here, give potential misleading evidence in favor of false high-level theories of various kinds, including classical physics, kind of a high-level theory with respect to quantum physics, and supernatural hypotheses. You can think of those as like a kind of high-level hypotheses about what's causing the walking on water. But you don't need those hypotheses in the sense that these are histories that are allowed by the unspooky, unsupernatural, straight-up quantum theory. So we can get misleading evidence here, and that's okay. Of course, it's okay unless we get it, but it's okay that it's possible that we get it. if we don't in fact get it. So what's the point of all this? Well, one thing we can do with these sorts of modally distant quantum events is to try to give an account of counterfactuals. So Lewis had this account of counterfactuals in terms of possible worlds. He ran into problems with it because he wanted to give an account of counterfactuals in deterministic worlds. And there seemed to be a problem. If things had been different in the deterministic world, while the laws had remained the same, then it seemed that there would have had to been a difference all the way back to the beginning of time. There would have been a difference in the initial conditions. And it doesn't seem plausible that, like, if I had wiggled my finger, there would have been a difference in the initial conditions of the universe. That doesn't seem true. And Lewis thought, well, we could be living in a deterministic world. And if so, that would need to be true, but it would need to be true without changing the initial conditions of the universe. So he introduces this idea of a miracle, a small violation of law which implements counterfactual antecedent in a kind of minimally disruptive way. And it seems like we can't avoid something like that if we want to have non-trivial counterfactual deterministic worlds. But it's not at all clear that we do need that, especially if we're dealing with quantum theory. Quantum theory is an indeterministic theory. And I think it's enough if we have an account of counterfactuals that works in the context of indeterminism, in the context of quantum theory, if we think that is in fact the right physics. Lewis didn't think that determinism was necessarily correct, but he thought that it could have been correct. And so we would need to understand how counterfactuals would work if it were correct. And in other work, I've questioned that. If all possibilities are indeterministic possibilities, then there just doesn't need to be a coherent account of counterfactuals that still works in a deterministic setting, because maybe determinism is metaphysically impossible. But we don't. So one thing we can do is give an account of miracles, these sorts of quantum events where they kind of simulate miracles, where what Lewis thinks of as a miracle is kind of happened as a result of a quantum indeterministic event. So like the kind of things that Lewis has in mind is like a kind of a particle jumping in somebody's brain to cause them to make a decision differently from the way they in fact made. Presumably there are quantum, like this, small quantum interventions on the position, on the locations of particles in one's brain that are going to likewise affect one's decision. So it seems like you could use these sorts of quantum modally distant possibilities as miracles in this sense. But I'm suggesting it's not particularly well motivated to do so, because the motivation for thinking you have to use miracles or something like them is coming from a need to handle counterfactuals under determinism, which we might not actually have to do. And anyway, there are like independent worries about the use of miracles. It doesn't seem intuitive that, like, if I had wiggled my finger, a miracle would have occurred. We often think that, like, actually the better thing to do is to track back further to where I made like a smooth and rational decision to wiggle my finger rather than made one that was caused by. And anyway, Keandor makes this point as well. So using these low probability quantum events as miracles directly, not so promising, though maybe you could do it if you wanted to. But they might still have other applications. So here's something I suggested in my last book, and I'm just going to suggest it in outline again here. If you don't want to use miracles, you might still want to use the possibilities that are described here and the probability distribution that arises from them. So it's not just the case in quantum theory that we have possible events corresponding to all these kinds of bizarre sorts of tunnelings. It's that we have a well-defined probability measure for what would the probabilities be if that tunneling were to occur. So it's not just like we get the tunnelings possible, but we don't know what goes on afterwards. we get that the tunneling is possible, and then we have a well-defined chance measure over it. And this chance measure, I think, can be used in the pursuit of an account of counterfactuals that doesn't have this kind of miracle involving form. This would be more in the spirit of the account of counterfactuals you get in the mentaculous style approach of Albert and Lower, where it's about finding out, identifying like histories that match the antecedent, and then looking at the probability distribution, the objective probability distribution that follows, that is over the histories that match your antecedent. And that sort of thing is something you can straightforwardly implement with the resources that quantum theory gives you, because it has this feature, it has this kind of universal probability measure built into the quantum state as the amplitude. So that's something I think it's not to develop a positive theory of counterfactuals in the quantum scenario, but it's to give the kind of resources, all the resources you could reasonably want in developing one. You've got histories which can branch at any time in these ways, and whichever way they do in fact branch, you've got a probability measure that comes out as well defined. So all of that is in the spirit of kind of, let's go for an account of counterfactuals directly. This is kind of what Lewis does. He says, we'll get an account of counterfactuals. Well, first we'll get an account of laws, then we'll get an account of counterfactuals, then we'll get an account of causation, then we'll get an account of loads of other stuff that's derivative on all that. But that idea of getting counterfactuals first and then causation is, I think, a shady one, a little bit suspect. An alternative approach is to kind of go causation first, or rather to kind of maybe to go for causation and counterfactuals as a package in this interventionist kind of way, rather than hope to first define counterfactuals and then causation out of the counterfactuals. So here's what Woodward said about interventions. These are the criterion for some events to be an intervention. So this is an intervention on X with respect to Y. I think this is what this is actually a definition of. And so the intervention has to be like a causal change on the variable that it's intervening on. It has to kind of turn off the influence of all the other things that would have affected the variable it's intervening on. So when I is an intervention on X, X is the variable that gets changed by your intervention I. And then there are downstream effects of the change on X, in particular, some changes in Y. And that intervention has to not have independent consequences for Y. And it has to be, broadly speaking, it has to affect Y only via its effect on X. And it has to screen off X from any other influences other than itself. And the thought is that if anything can meet the criteria for an intervention, these sorts of quantum interventions, these very low probability quantum events can do that, because one can specify as part of the kind of microstate that at the end that one wants to get to, that there were no other effects of the intervention on the kind of end state. And there will likely be some non-zero chance of that specific history, that the microhistory that you describe that meets the conditions from a given state that we might start out in. And effectively, one can just kind of build in to the intervention that it is a change on the variable you want, and that the other thing and the features you don't want change do not change. And so you kind of stipulate that the micro history you want has the features you want, and then you can be sure that there will be some non-zero probability microhistory with that feature. And yeah, I mean, this is not obvious that this is correct, that there won't be some problem with like these interventions being insufficiently surgical, like they'll kind of mess up too much when you try and change one thing, you kind of inevitably change some other stuff as well. But on this sort of view, there isn't like a problem coming specifically from quantum theory for these events counting of interventions. It may be that, you know, there's just no such thing as an intervention Woodward describes, but if so, it's not because of something that kind of metaphysically possibly could happen, but quantum theory prevents it happening. Doesn't seem to be the what's going on here. This is all very rough, as I said. I'm grateful for you listening to this work in progress. So here's a couple of explanations of the interventionist kind, where it looks like we might have these quantum interventions actually supporting genuine explanations. Here's one. We want to explain why the atom of, I don't know, helium is stable. And we might say, well, the total charge on the nucleus is balanced with the total charge of the electrons as part of that explanation. And then quantum intervention, one of the protons leaves, it tunnels a long way away. And the atom is no longer stable. It's got a charge instability. It's going to lose one of its electrons very quickly, and maybe some of its neutrons too. And so even when in fact no such tunneling occurs, the idea is that the fact that this intervention could occur grounds the causal fact that holds even when it doesn't occur. That is, that the stability of the atom is being caused by the charge in its nucleus, or maybe by the balance of the charge in the nucleus and the electron cloud, or something like that. That's one kind of explanation which we think actually holds, but it could be that its actual holding is grounded in a very unlikely quantum event which doesn't occur. Similarly, and now scaling things up, this is an example that Woodward considers and puzzles over, because it's kind of hard to understand how you can intervene on the moon without also intervening on loads of other stuff. So he has this idea that the moon's orbit, features of the moon's orbit cause features of the tide. And then the idea is that if you intervene on that by having all the moon's matter particles simultaneously quantum tunneling a really long way away, then you will no longer get any tidal phenomena. So it's in virtue of the fact that if that intervention occurred, the tides would cease, that we take it that the tides actually are caused by the moon's orbit, even in cases where it doesn't, nothing tunnels at all. So these possible very unlikely events are playing a role in grounding actual explanatory dependencies. That's the claim. And obviously, having these interventions available helps this story, because if we didn't have that intervention available, then we might struggle to think of what the intervention here could possibly be. And Woodward actually does struggle a bit to explain what that intervention could be like. So now we'll just scale this up for the last part of the talk to the cosmological scale. So I was just making the point that some of these interventions are needed to underwrite cases of explanation which we think in fact hold, even when the events which we're taking to partly underwrite them are vanishingly unlikely to happen and do not in fact happen. Nonetheless, the fact that this could happen, this quantum intervention, it plays a role in grounding explanations that we think do in fact hold. And if you take certain kind of global types of causal explanation, then it turns out that the kind of quantum possibilities you need to consider are really, really radical. So consider explanations that rely on the dimensionality of space or space-time. So Ehrenfest has this famous argument that you wouldn't get atoms or planetary systems being stable if it wasn't for the dimensionality of space being 3. And Tegmark has a paper where he kind of takes that kind of argument on and generalizes it, and argues that in space, in higher space-time dimension, you don't get hyperbolicity, so you don't get predictable physical behavior. You just can't do physics at all in sufficiently high-dimensional spaces. And so it looks like prima facie, it's the three-dimensionality of our space that explains the stability of atomic and planetary orbits, and it's the three-dimensionality of our space that explains the predictability of physical behavior. How can interventions understand that? It looks like dimensionality just isn't the kind of thing you can intervene on. Well, if you take those sorts of worries seriously, what you may end up doing is diluting interventionism, and that's what Woodward, I think, does. He talks about the interventions being conceptually possible, which basically means you can kind of imagine them clearly enough and know what you're doing when you do that. But that really undermines the realist credentials of his account. And it's something I've talked to Noelia Renata Rivera a lot about, and had material on this in Noelia's thesis. If you want to maintain interventionism as a robust realist theory of causation, it looks like you need the possibility to be a robust realist notion of possibility. And if conceivable interventions are okay, then that is too damaging to the realist credentials of the view, I think. But it's not obvious how we could have a genuinely possible intervention on dimensionality. But turns out quantum theory might have the answer for us in certain cosmological scenarios. If you have a kind of string landscape model, then what you've got is a high dimensional 11 or 26, probably 11 in most popular models, dimensional spacetime that compactifies down so that many of the dimensions kind of get rolled up and ignored, and only a few of them remain physically salient. And the explanation of our world being 3 + 1 dimensional is that in our world, those 11 compactified down to 3 + 1, but they could have compactified down to a different number. And even if it compactifies down to 3 + 1, there's still a lot of ways that can happen. Apparently around 10 to the 500. And what this involves is, the way I envisage it, is that the universe is kind of doing this kind of random walk over a surface with lots of holes in it. These are the minima. And the universe will fall into one of these minima and then stay there. And so like things will remain 3 + 1 dimensional forever after, once the universe has fallen into this one of the 3 + 1 dimensional minima. But tunneling is possible, albeit very unlikely. The entire universe could tunnel into a different minima of the string landscape, and the dimensionality of space-time would then change. The effective dimensionality of space-time. So then the effective stability of orbits would change. So here is, the entire universe quantum shifts its dimensionality by moving to a different part of the larger multiverse of like the landscape of possibilities. That's going to have really drastic consequences for the physics of our world. Yes, orbits are certainly going to be unstable now. Maybe too much is going to change. Maybe this isn't the case where surgicality can't be sustained. Maybe this is actually a problem for this account. Would an intervention be sufficiently surgical? Well, it depends. whether there's a minimum of the string landscape, which has a different number of dimensionalities, different number of spatial dimensions from ours, but in other respects has physics that are enough like ours. And although I've hardly started thinking about this at all, my suspicion is that it might be just a kind of open question in string cosmology right now. We just don't know enough about the kind of statistics of the different minima of the landscape to know whether there are places it could tunnel to that would be sufficiently surgical. I don't know. I'm not a string theorist, as you can probably tell, but nonetheless, I think it's interesting to think about. So yeah, we're done. Summary, even in classical possibility physics, we've got a range of modally distant possibilities. They can be used in these constructive projects. Quantum physics kind of supercharges that by giving an even wider range of low probability physics and possible outcomes, by making sure there's a universal objective probability measure that is kind of conditional on, that kind of is forward-looking from any of these happening, and potentially, at least in string landscape models, permitting these really weird kind of interventions that have no classical correlate at all, and potentially have application in some of these like global causal explanations in terms of dimensionality of space-time. All right, that was a lot. Thank you. I'm done.